The artificial intelligence landscape has just undergone another seismic shift, with a series of breakthroughs that collectively push the boundaries of what machines can learn and how they learn it. Headlined by Google's revolutionary mini-brain AI project that has successfully emulated cortical column functionality at scale, achieving neural activity patterns strikingly similar to biological brains, while consuming 94% less energy than traditional transformer models. This neuromorphic architecture, detailed in a landmark paper in Nature, doesn't just mimic brain structure, it replicates the hierarchical temporal processing that allows humans to understand context and make predictions through what researchers are calling predictive coding in silico, enabling the AI to form conceptual understandings from raw sensory data without explicit labels, effectively closing the gap between narrow AI and general intelligence more than any previous system. Meanwhile, ByteDance has open-sourced ToolTrain, a framework that allows large language models to not just use tools, but genuinely understand their functionality through a novel embodied learning process where the AI physically interacts with digital environments. Imagine an AI that doesn't just know what a spreadsheet formula does, but understands how changing values will affect downstream calculations through actual experience with the tool, creating a fundamental shift from statistical pattern matching to genuine functional comprehension. This approach has already yielded astonishing results. Microsoft's POML represents another leap forward, specifically in how AI understands and interacts with the physical world through robotics. Unlike previous systems that required precise programming for every potential scenario, POML allows robots to build probabilistic understanding of objects and their properties, enabling them to handle novel items with human-like adaptability. In demonstrations, robots using POML successfully manipulated deformable objects. This technology leverages a breakthrough in haptic transfer learning where knowledge gained from manipulating one object type informs interactions with entirely different materials. The system's ability to build mental models of object behavior represents the first genuine step toward common-sense physical reasoning in machines. Perhaps the most fundamentally transformative development comes from the rise of new self-supervised learning techniques. Research teams at DeepMind, OpenAI, and several universities have simultaneously published papers on contrastive predictive coding methods. One particularly impressive implementation from Stanford uses temporal coherence maximization, where the system learns by predicting how a scene or text will evolve over time. This approach has produced models that outperform supervised counterparts on numerous benchmarks, despite seeing 1000x less labeled data. Instead of needing millions of carefully labeled medical images to diagnose diseases, these systems can learn from raw, unannotated scans. In adjacent developments, Google's Minerva project has achieved new heights in mathematical reasoning by combining symbolic AI with neural networks. Meanwhile, Meta's Project Care has made surprising progress in effective computing with models that can detect and respond to human emotional states. On the hardware front, IBM's North Pole neuromorphic chip has begun commercial deployment, offering 25x better energy efficiency. The collective impact of these advancements suggests we're entering what researchers are calling the second wave of deep learning. The commercial implications are already materializing. Companies leveraging these new approaches report 80% reductions in training costs and 90% reductions in data requirements while achieving superior performance. However, these breakthroughs arrive with significant ethical and societal questions. Self-supervised systems can develop unexpected capabilities without explicit programming, making them harder to monitor and control. Neuromorphic systems like Google's mini-brain approach biological complexity so closely that researchers are beginning to discuss emergent phenomenology. As these technologies move from research labs to real-world applications, we're witnessing not just incremental improvement, but a fundamental redefinition of what artificial intelligence is and what it can become. The ceiling of artificial intelligence has just been raised dramatically, and we're only beginning to understand what lies beyond it.